Okay, this is considered an optional video from AP Physics C Mechanics course. The reason it's optional is simply because simple machines are not really part of our curriculum, but I still like to cover this just simply because, one, it's covered in my general class and in my one semester class, but two, it does a really good job of illustrating the importance of understanding efficiency, which is, even if it's not part of the AP curriculum, it's really very important to the way the world relies on energy transformation and just so much of that is related to efficiency that I want to make sure we at least talk about it. So no easier way to understand efficiency than by looking at simple machines. Now, simple machines are something that oftentimes are studied in grade school, and then you might even start to do some things with simple machines in middle school, like the pulley system and the inclined plane and things like that. Well, in high school physics, we oftentimes start to look at how we start to use these things to actually do something useful and be able to design machines to be able to accomplish a particular task and so forth. So let's go ahead and just jump into this and see what happens. Simple machines make work easier by changing the amount of force and distance. So it's sort of a very general definition for what a simple machine is. Let's try to understand that in more detail here. Again, work here is a force through a displacement. That goes back to our definition for work. Simplest definition, work is equal to F times D. We can throw that cosine of theta in there as we talked about before, but let's go back to just that simplest definition, force times displacement. Now, for example, you get a flat and you need to change a tire. Do you need to use a jack, sometimes called a screw jack there, because you don't have the energy to lift the car, or because you can't exert the force necessary to lift that car? And the answer to that question is that you need to use that jack because you can't exert that force directly to be able to lift that car. It's just too heavy and we don't have that strength. But we certainly have the energy to do it. We can certainly do the work necessary to lift that car. I do that anytime I have to change a tire. But you use a machine to be able to accomplish that task. What most machines do is they multiply force, but they cannot multiply energy. They can't make more energy than what you put into that. So we can't create or destroy energy, but we can transfer it. In this case, what we're going to do is we're going to use that machine to be able to transfer the energy that I use here to be able to use that energy. Now, most machines multiply force, but they can't multiply energy. They can't make the work that you do greater. They can just change the amount of force and distance. Now, let's go ahead and see if we can't understand that better with a simple schematic. So let's just draw a little block here representing a simple machine. It could be one of our six. And those six, again, are shown here. Every simple machine has some sort of input work and some sort of output work. So I'm going to just draw some arrows here representing sort of like a flow chart. So the input work, often called the effort sign. This is the sign that you work on. So we could say that the input work is the effort force multiplied by the effort distance. Now I'm going to go ahead and make that D a really big value, and you'll see why here in a little bit. So work is force times distance. I'm going to exert some sort of effort force through some sort of effort distance. Now what the machine does is it allows that force to become much bigger. But it does that I'm going to call that the resistance side. It does that by making the distance that force acts much smaller. Okay, so what we see is a force multiplier. So the output force becomes a lot bigger. It just comes at the expense of a much smaller distance. Okay, so this is the idea behind a simple machine. You notice the amount of work that I do ideally would be exactly the same, but my force becomes bigger but that comes at the expense of the distance becoming smaller. Again, I cannot increase the amount of work that I do, but I can change that amount of force. That just comes at the expense of a smaller distance. Okay, and so the basic idea of a simple machine allows us to do work more easily. Now, the performance of a machine is described by something called mechanical advantage, and perhaps you've heard of this term before. We often abbreviate it as MA. There's two different kinds of advantages that we can look at. One is an ideal mechanical advantage, and the other is an actual mechanical advantage. Let's go ahead and write an equation up here again to begin with. You see that there's two portions of work. There's a force and a displacement. Well, ideal mechanical advantage is a ratio of the displacements. You might even just say distances, since the displacement and the distance would be in the same direction there. But yeah, it's a ratio of distances. Now, here is a lever, a very common, simple machine, very useful for lifting heavy objects. This person here is exerting some sort of force through this distance. And since ideal mechanical advantage is ratios of distances, let's say that this is the effort distance. And so he moves this thing down quite the distance there. I'm going to call that d sub e. And in the process, from that fulcrum, the other side of that lever moves up only a little bit. So I'm going to call this d sub r, the resistance distance. So the IMA is a ratio of displacements. It actually, the IMA, I could write that as a ratio of effort to resistance distance, so dE over dr. The IMA, ideally, it's a ratio of these distances. It is how far I exert that effort compared to how far the resistance moves. Okay, so that'd be the IMA. Now the AMA is actually a ratio of forces. Again, it's the other side of that equation, right? We have either forces or displacement. So the actual mechanical advantage is ratios of forces. Let's go ahead and draw that over here. The whole idea behind that lever is that he's able to exert a rather small force. We call that the effort force. But in that process, the machine transforms that force into something much larger. So we're going to be able to get out a much larger force here. I'm going to call that the force of resistance. So ratio of forces, if I want to get the AMA, it would be the resistance force divided by the effort force. Now you got to be careful here because you notice in one case the AMA has the resistance over the effort. In the other case, I have the effort over the resistance. So be careful there. And again, the actual is a ratio of forces. The ideal is a ratio of displacement. So let's go ahead and do a quick numerical example. You lift a 1,000 Newton boulder by exerting a force of 250 newtons on the lever. Okay, so this would be 250 newtons over here, and you are lifting a 1,000 newtons boulder. The long arm is pushed down a distance of 1 meter, and the boulder lifts up 0.2 meters. So if I want to determine the IMA, again, the IMA is a ratio of effort to resistance, and what I get there is 1 meter divided by 0.2 meters, and that's 5. Now there's no units on this. Notice it's just a multiplier. What I'm saying here is that ideally I would get 5 times the advantage here, right? I'd be able to get, I'd have to push this thing through 5 times that distance. I'd get 1/5 of that over here. That's the ideal mechanical advantage of 5. Let's take a look at the actual mechanical advantage. Well, AMA is a ratio of forces. So in this case here, it's resistance to effort. Well, resistance, I know that's 1,000 newtons. And I'm putting in 250 newtons. Well, you notice that that's actually only 4. And the reason for that is that I never get as much work out as I put in. I have some forces that are going against things like friction and things like that that reduce the overall advantage of that machine. Okay, and that has to do very much with this concept called efficiency. So this is about an 80% efficient machine. Let's see how we can define that here. Now, IMA is always going to be greater than the AMA because of internal friction of that machine. And so we never get as much work out as we put in. Let's go ahead and see if we can't come up with an equation for that efficiency. And you see how it's related to these IMAs and AMAs. Work out, let's go ahead and use some of our color coding up here. Work out would be the resistance force multiplied by the resistance distance. And I'm going to go ahead and draw those using the color coding that we have up there. I'm going to divide that by the work in. Well, the work in is the effort force multiplied by the effort distance. Okay, so again, just going with my definitions of input and output work. Now I want to regroup these things. Instead of considering FR associated with DR, I'm going to go ahead and just try to group these things this way. So I'm just going to do a little bit of reorganization here and group these with different things. Thank you, associative property of multiplication and division. So you notice that FR over FE is actually what we define as the AMA. So I'm going to go ahead and write that as the AMA, is that first portion. And I notice that DR over DE is not the IMA, but it is the reciprocal of that. And lo and behold, I get a nice definition for efficiency, or a nice way of calculating it. It's AMA over IMA. And I can see by looking at this, I was expecting to get 5, I only got 4, that's 80%. So for this particular example, the efficiency of this machine is 4/5, or about 80%. Okay. Ideally, what we would do is we would try to reduce the amount of friction, maybe using some oil in our machines and so forth, to be able to reduce the frictional losses and try to improve the efficiency of those machines. Okay. Now, last thing for us to look at here on this lesson is to look at the IMA of various machines. The IMA is something that can be obtained just by looking at the machine itself. Of course, the AMA depends on just how much friction is acting there, but the IMA is a function only of the machine and this of the machine design. So let's take a look at the common lever. If I wanted to determine the IMA of a lever, it's really just a ratio of the effort length to the resistance length. So I can actually just look at a lever and look at where that fulcrum is to get the IMA. Okay, and again, if you want to think of this as a ratio of distances, we can certainly do that. The idea here is that when I move this thing through that kind of distance, if this is on the effort side, what I get on the resistance side is a much smaller distance there, and that's simply because of where that fulcrum is located. But just using this idea here, you can see that the ratios of these lengths are going to be exactly the same. And I can look at this and say that the ratio of this one to that one is in the same ratio as this one is here to that one, right? So it's far easier to just look at the effort lengths and the resistance lengths as the distances from the fulcrum to the endpoint there, as opposed to having to consider how far you're moving that thing up or down. Okay, so it just be LE over LR. Now, the inclined plane is another simple machine. And if you think about what an inclined plane does, we know that an inclined plane makes things easier to sort of lift them up, right? We reduce that force of gravity by sort of resolving that thing into a weight force down the plane and a weight force into the plane, right? So we have an Fg sub x and Fg sub y. Well, we could certainly resolve that. But at the same token, we can also look at this as a ratio of distances, right? We can look at it as an ideal mechanical advantage. This right here would be the effort distance, and this right here would be the resistance distance. It's like I'm going to be able to lift that thing up so far, but I'm going to do that by exerting a much smaller force to a much bigger distance. So the IMA is just a ratio of that length of the incline to the height of that incline. Okay, so that's the ideal mechanical advantage. And again, you might have had a hard time looking at force, the weight force being resolved into its components. You notice it's really just, we can think of it very simply as a mechanical advantage of L over H. Wheel and axle. The common steering wheel is a wheel and axle. You put your hands on the outer portion of the wheel, and inside the center of that is the axle that you're trying to turn. That shaft inside goes underneath the hood, and it's really difficult to do. So we need a mechanical advantage to be able to do that. Same thing happens on a door handle. Right? You put your hand on the outside portion of the door handle, and then the inner axle then turns the mechanism. That's actually quite hard to do. So mechanical advantages. Wheel and axle. The ratio of the outer radius to the inner radius, right? So the ratio of the radius of the wheel to the radius of the axle. Of course, I could also do this as a ratio of diameters, right? I could do big D to little d, I can also do big circumference to little circumference, right? So all of those are going to be in the same ratio. Now the wedge is very similar to an inclined plane. It's just almost like a double inclined plane. The wedges are sort of difficult to actually simulate in the classroom and actually measure. Oftentimes, if we have time, we would do a lab that is looking at simple machines and measuring their efficiency. It's just sort of difficult to do that with a wedge in the classroom. Certainly, if you've ever split wood, you're using a wedge to be able to do that. The doorstop is another example of a common wedge. Pulleys, we've seen pulleys before. A pulley is another one of the simple machines. If you look here, I have a single strand of rope supporting the load. N is one single rope. Here I have a single pulley, but you notice I have two ropes that are supporting that. If I pull upward on this one with 50 newtons, well, this also pulls up with 50 newtons. And so I can lift a 100 Newton load using that pulley set up that way. And the reason for that, again, is because of the way that that pulley sort of multiplies my force. Of course, if I lift this thing up 20 centimeters, this thing's only going to lift up 10 centimeters. And again, because each time I do this, I'm going to get a bigger force out, but a smaller distance. Okay, so N is equal to 2, the number of strings that are supporting that load. Over here, I have a complex system, sometimes called a block and tackle, but you notice I got 4 of these strings that are supporting the load. And so N is equal to 4. IMA, the ideal mechanical advantage on this, is simply N, the number of strings supporting that load. So I can get 4 times the force here, but it comes at 1/4 the expense of 1/4 the distance. And finally, the last one for us to look at to complete this video on simple machines is this one over here. It's the screw jack. And the screw jacks are very common to give very large IMAs. And the reason for that is that this handle, oftentimes going through some sort of rotational motion here, has a really big motion, right? When I put that handle, turn that handle all the way around through a circumference of 2 pi r, that'd be how far my hand moves as I move this thing around through there. This thing only goes up 1 thread length here, right? And that thread length is often called the pitch. So the IMA is actually just a ratio, again, of input distance to output distance. And so you can see that it's a ratio of the circumference, 2 pi L, where L represents the length of that bar, divided by P, the pitch. And you'll see screw jacks oftentimes have a very large mechanical advantage. If I want to lift this car up, I'm going to do that by exerting the force on this handle. It's going to be a small force, but it's going to be going through a really big distance. Right? So small force, big distance, and what that's going to do is it's going to exert a really large force, but through a small distance. Okay, and so that's the idea behind that screw jack. Again, simple machines, they just make work easier by being force multipliers. And the connection, again, with simple machines and efficiency is why I still think this is an important topic for you to understand in AP Physics. And that completes this lesson.